Let's start by evaluating sine of arctangent of 1. We'll start by working on the inside of the composition. Arctangent of 1 is the angle in quadrant 1 that you have to plug into tangent to get out 1. So if the output is 1, then the input was pi over 4. So that means that arctangent of 1 is pi over 4. And now we're left to evaluate sine of that angle, sine of pi over 4. So sine of pi over 4 is radical 2 over 2. Now let's evaluate tangent of cosine inverse of 3/5. So again, we're going to start on the inside and we're going to think about what angle do I plug into cosine to get out 3/5. Well, 3/5 is not one of the outputs that we're familiar with. It's not from our standard quadrant 1 outputs of our standard angles. But that doesn't mean there's not an answer. There's some angle that you plug into cosine to get out 3/5. So let's take a second to call that angle theta. So that this problem becomes finding tangent of this angle theta. So I'm going to pull this work off to the side and say theta is equal to cosine inverse of 3/5. So now let's take cosine of both sides. So cosine of theta equals cosine of cosine inverse of 3/5. Well, cosine and cosine inverse cancel, so I know cosine of theta is equal to 3/5. And from that, I can construct a right triangle with this interior angle theta and the knowledge that cosine of theta adjacent over hypotenuse is 3 over 5. The adjacent side is 3 and the hypotenuse is 5. So if I have a triangle here with two side lengths next to this angle theta, I can evaluate tangent of theta if I just find the missing side length. So tangent of this angle theta is opposite over adjacent, so I have to find this missing side. And this is actually a nice right triangle that follows a Pythagorean triple that makes this missing side 4 from the Pythagorean theorem. Since the hypotenuse was 5, the side lengths are 3 that correspond to it. If this was 3, this one has to be 4. So tangent of theta is now, again, opposite over the adjacent side. So tangent theta is equal to 4/3. Finally, the last one, we're not actually going to evaluate. The answer is not numerical, but the instructions say write as an algebraic expression. The process we're going to use, though, is similar to our previous evaluation. This is a trigonometric expression, so cosine of sine inverse of x over 2. We want to turn it into an algebraic expression, so essentially get rid of cosine and sine inverse somehow. So the idea is that sine inverse of x over 2 is some angle. And so let's take a second to call that angle theta. Then this problem becomes find cosine of theta. Well, if theta is sine inverse of x over 2, then we know by the definition of an inverse, right, that sine theta is equal to x over 2. That idea of taking sine of both sides. So let's construct a right triangle with the angle theta. And what we know is that the opposite side has length x and the hypotenuse has length of 2, opposite over hypotenuse. So if I want cosine theta, I need this adjacent side over the hypotenuse. So I have to solve for this adjacent side. Let's call it b. So we have b squared plus x squared is equal to 2 squared. And I'm going to highlight b to remind myself that that's what I'm solving for, because it could get a little tricky since there are two variables involved. So to isolate b, I'm going to subtract x squared to the other side. So I have b squared equals 4 minus x squared. So b equals plus or minus the square root of 4 minus x squared. And so we're going to go ahead and say b is positive the square root of 4 minus x squared, which, just as a quick note, this does not simplify to 2 minus x. I can't take the square root of each piece separately. So we're going to say this side length, right, is the square root of 4 minus x squared. So cosine becomes adjacent over hypotenuse. So we'll have the adjacent side to theta as the square root of 4 minus x squared over the hypotenuse 2. So we've gone from a trigonometric expression to an algebraic expression. So we have x raised to a power, and we have a root function, but there's no more trig functions involved.